All right, so we're moving on to voltaic cells. So now that we've learned all about redox reactions, we can now apply it to a voltaic cell. And voltaic cells will always be made up of two electrodes. One will be known as your anode. And what is important about the anode, it is a site of oxidation. And the other will be known as your cathode. And here it is the site of reduction. So we can apply what we know about cells and show what's happening within a voltaic cell. And what's important about this is it will turn chemical energy from the chemical reaction into electrical energy. So we're gonna take a look at this voltaic cell with what's reacting at the top here. And we have our two half cells. What we want to figure out is what piece of metal is at the anode and what piece of metal is at the cathode. So you would want to take a look at your data booklet, so over here, and we would see that in terms of metals that we have, where is it here? Silver solid is here and copper solid is below it. So when we're looking at what's our strongest reducing agent, it is going to be copper solid. So copper solid is our strongest reducing agent, and that we can also compare our ions, and the silver ion will be our strongest oxidizing agent. So if I was to look at my silver ion, it is there, my copper ion is here. So the silver is higher than the copper, so that one would be the strongest. So with that, we can now figure out what is our anode, what is our cathode. Because if you are a strong reducing agent, you are undergoing oxidation. So here, our anode will be copper solid, which would mean silver solid is at the cathode. So that's the first part, and now we can label everything else. So if copper solid is this anode here, then its ion needs to be in solution. So you'll have copper 2 positive, and we would have something negative to be floating around in here with the copper solid, so like nitrate. And then on the other side, we know that silver is our cathode, and so its ion, silver positive, would be in here as well. And I'm just going to write nitrate as well, but it could be any spectator ion that's just there to help facilitate the reaction. So this is our first part, and now once we have labeled what we need, the rest is going to be the same for all voltaic cells. So all voltaic cells have electrons from the anode going towards the cathode. So for this to happen, because this is a spontaneous reaction, we also had to complete the circuit with the salt bridge. So that's important to make this whole thing react. If you remove the salt bridge, nothing will happen. And in a later video, we'll figure out how to calculate the voltage that every cell could generate when we're putting two half cells together. So in my half cell at the anode, my copper and my copper 2 positive, what would be happening here if something's undergoing oxidation? We know that's going to lose electrons. So this copper solid right here is going to break apart into copper 2 positive and 2 electrons. I should just maybe put it like that, plus 2 electrons. So when this breaks apart, the copper solid would be losing mass. So as it's breaking apart, this anode would be getting smaller and smaller. It's losing mass. So we'll get this copper 2 positive has to go somewhere, so it will go into this solution, and those electrons will be what's moving from the anode over to the cathode. Now, on the other side, the cathode, it is gaining electrons, right? And that's what reduction is. Reduction, we know, is, if we're looking at Rig, the gain of electrons. So as electrons come over here, it is going to attract the positive ions from the solution. So on the cathode, we have electrons coming over, we have those positive ions from the solution coming together, and it's going to form silver solid. So when this happens, this is coming out of solution onto the solid with those electrons, and we are going to be adding mass because we are forming a solid. Now, that's the basis of how the cell works. Anode loses electrons, comes over to cathode. We can tell what's undergoing oxidation, what's undergoing reduction. And then lastly, to complete the cell, we have that salt bridge. So when we're looking at this copper 2 positive being added to solution, it is going to build up a charge that is positive. So to neutralize that, these negative chlorine ions from the salt bridge are going to come over and neutralize those charges. And then the same thing is happening on the other side. As these positive charges are leaving, this negative charge would be greater. So those positive ions from the salt bridge can come over and neutralize that solution. So that's how we are always moving your electrons anode to cathode from the salt bridge. The positive ions move towards the cathode, the negative ions move towards the anode, and then we have our complete voltaic cell, and we'd be able to apply all of our redox reactions to the cell. Now, just to point out one last thing from our data booklet, and we have seen this before, if your OA, which was silver positive, is higher than your RA, which was copper positive, that reaction is spontaneous. So that's what's happening in here. Our OA is above your RA, so you have a spontaneous reaction, and spontaneous reactions mean you will get a voltage. So you'll get a cell voltage. And again, we'll learn how to calculate that later on. I hope this was helpful. Please stay tuned, and we will look at electrolytic cells next.